Hey, welcome back to the second video. Right, still remember that this is a video. This is the material we are using for the video. Okay, some materials there, so make sure you can read it, go into that and compare things. Okay, all right. So we talked about the basic properties. Okay, so in any experiment, your event, if it is a possible event or a certain event, then that probability should give you a 1. Okay, if it is impossible, then you should have a 0. Okay, all right. Now, steps in forming a probabilistic model. Okay, now when you want to make any model, you want to set up a model, look, you have to follow these steps. Okay, now probabilistic model, in the sense that you want to be able to compute probabilities with your model you will calculate, you will get. Okay, so in that case you should follow these steps. The first thing is your sample space. Make sure you know your sample space. Okay, you know where your outcomes are coming from. Okay, you know where your outcomes are coming from. Okay, and then algebra of event. Okay, know all the possible sigma algebras, and then know the probability measures. Okay, there should be some probability measures. Okay, so in that case, any probabilistic model should have a sample space, the sigma algebra, and then the probability measure. Okay, in that case you can call it a probability space, and then that probability space can be used to compute probabilities and then be able to analyze whatever model whatever thing you want the model to be doing. So sample space in general, consider an experiment whose possible results are included in a finite number of outcomes. So remember, we talked about sample space. So these are the possible outcomes that they are likely, because that is what can happen in an experiment. Okay, all right. So we do not need to know the nature of these outcomes. Okay, only that there are a finite number of n of them. Okay, so we call n1, w1, omega1, up to omega n elementary or sample point. Okay, so the sample space is just everything. It's just everything that is possible to count. So when you toss a fair coin 3 times, this is all the possible things that might happen. Okay, so the choice of a sample space is the first step in formulating a probabilistic model of an experiment. So you have to do that. You have to be able to know your sample space. Okay, so you are tossing a coin 4 times. What's your sample space? Try figure it out. Okay, all right. Now, algebra of event. Okay, so a set of events f, or a collection of subset of omega, is a sigma algebra. Okay, which is a collection of subset of that with the following properties. So now what we are trying to say is that, okay, now when you know your omega, which is your sample space, okay, it contains element, isn't it? So it contains element. So you try to pick some subsets. Remember that subsets of omega are going to be events. They are going to be event. Okay, they are going to be somebody's interest. Okay, so I can say that my subset, one of my subsets, can be something that contains head, all right, head, tail, head, tail, head, and in my event in English will be that the first outcome is a head. Okay, so we see that I have a subset, and that subset is a collection of events. Okay, it's a collection of events. So if you have subset of the main omega, which is the sample space, which obeys the following properties, or which have the following properties, then we can call the set of events, or the collection of these subsets, as a sigma algebra. Okay, as a sigma algebra. So the first thing is that in your sigma algebra there should be that empty set. Okay, the empty set should be in the sigma algebra. The empty set should be in that sigma algebra. So if you say it's a subset of omega, obviously the first subset of every set is an empty set. Okay, empty set. So if you are trying to have the collection of various events, okay, into a sigma, into a set, and that set is, we are calling it sigma algebra, then it means the empty set would surely be there. All right, and then if you have event A in F, then you expect its complement, okay, should also be in F. That means closed under complementation. And then if you have A1, A2, AI, then the union should also be in F. Okay, all right. So that is the properties that it has to obey before you become a sigma algebra. So these are additional properties. All right, the set itself must be in the sigma algebra, and then if you have A1, A2 up to AI, the intersection should also be in F. Okay, so all we are saying is that now you have a set. All right, let's say you are tossing a coin once, so you have head and a tail. These are all you have. Right, so this is a set you have. So what are the possible events? Okay, so the possible event is that I can get the empty set 1, I can get a head, can get a tail, then I can get the set itself, head and a tail. Right, so now if I collect this into a new set, and then this set I have obeys these conditions, then I can call this collection of subsets as what? Sigma algebra. So I find out that my first, which says empty set, should be in that empty set is there. All right, and then the set itself should be there, so the set itself is there. All right, is there. And he's saying that if I pick A and it's in F, its complement should also be in F. So if A is the H, the complement of H is T, which is inside. If I pick HT, the complement of HT is empty set, which is also inside. So this condition 2 is satisfied. If I pick A1, A2, the union should be in the set. So if I pick empty set, H and T, when I union this, I'll get HT, and it's in the set. If I pick T and then empty set, if I union, I get T. Is in the set. So whichever thing I do, the union is in the set. And then the intersection 2 is in the set. If what's the intersection of H and T is empty set. Intersection of empty set and H is empty set. Intersection of H, HT and T is T. So everything in the set. So I can call this as my sigma algebra. Alright, I can call this as sigma algebra. Right. So that's it. That is the definition for sigma algebra. Okay, so example, given that you have 1, 2, 3, answer the following numbered questions that follows. So is F naught, which is containing only empty sets, and this a sigma algebra? Okay, so this is a set, and then we are saying that F naught is containing only the empty set and the set itself. This is sigma algebra. We have to check using the rules. So the rule says that the empty set should be in F. Of course, the empty set is in it. The set itself should be there, and it is there. If I take the intersection of empty sets and then the set itself, 1, 2, 3, I get a empty set. If I take the union, I get back the set. Alright, if I take the complement of empty set, I get the set. If I take the complement of the set, I get empty set. So this is actually a sigma algebra. Okay, so that's a sigma algebra, because remember that the empty set is there, and the complement of empty set is what? Omega. And then if omega is in that, the complement of omega is empty set, which is also in F naught. And then if F naught is there and then omega, all of these are in the intersection, the union is omega, which is also in a set, and then the intersection too is there. So we call this a sigma algebra, and it's trivially true. That's a trivial sigma algebra. Okay, and it's asking, is this one to a sigma algebra? You have to compare using the conditions. So for per the conditions, empty set is there. So what's the complement of 1 is 2 and 3, which is there. What's the complement of 2 and 3 is 1, which is in F1, right? When you take the union of 1 and 2 and 3, you get 1, 2, 3, which is there. Alright, so therefore you say that F1 is a sigma algebra. Now, can we say F2 is a sigma algebra? Let's look at that. So the complement of the empty set is there, but remember the set itself is not there. Okay, the set itself is not there. So if pair that, you can even say it's not a sigma algebra. Alright. So these are another proof which is talking about sigma algebras. Right. Alright. So that is it for sigma algebra. So we'll talk about generator of a sigma algebra.